Alright, I believe this is the last one of the chapter, Geometry. It's about the ratios of areas. Before I forget, I've been forgetting that sometimes in these last few videos, here's your video questions you're going to have to answer at the start of class. Now, this is a quiz day. You're going to have some review before the quiz first, but after the video of 11.7, you should be able to answer these questions. So I'll give you a second to look at that. Okay, so what's this about? Well, you know what, the last few sections we haven't had any real theorems, which has been kind of silly, actually, because we've learned a lot of formulas in the last few sections. I don't know why they didn't call those theorems, but they didn't. They reserved theorems for something important, I guess, which is this, which is kind of a strange relationship. It's saying, well, if I know... Okay, these are both squares. If I know the relationship of the lengths of this, these sides to these sides, say this is x and this is k times bigger than x, the ratio of their areas is not that this is just going to be k times more area than this. It's actually k squared times more area than this. I have a little example here in the notes that if these sides were 8 and these sides were 12, well then this area would be 64, this area would be 144. That's not just, 150% of this one. I mean, 8 to 12 is like 2 to 3, or like, this is 150% of this. 2 to 3 in length becomes 4 to 9 in area. In other words, I got to square that ratio to figure out what this area is. What's kind of powerful about that is then you can find ratios of things you have no idea how to find the area of. Like, we don't have an area formula for the area of Isabella. So if we just happen to know that her height in pixels, which is what they measure cartoons in, probably in digital animation studios, if her height was actually 200 pixels somehow, and this one's 160, well, I know the ratio of 200 to 160. If I knew her area happened to be 800, I can't just assume that, oh yeah, you take 200 times 40 and you get this thing. Well, no, I don't know, because there's like all these funky shapes, and she's not exactly a rectangle and all that kind of stuff. So I just know that she's 200 high and her area is 800 square pixels. And if I know this one is 160, well, I can't just multiply by 40 or like try to figure out what that other dimension is that you multiply by here. What I should do is go, okay, 200 divided by 160, that's 5/4. So the ratio of this is 5 to 4. Or in other words, if I took this one times 5/4, I would get that one. Or if I took this one divided by 5/4, I would get that one. That just means, well then, for area, I should take this one, not just divide by 5/4, but I should divide by 5/4 squared. 5/4 squared is 25/16. So I need to divide by 25/16 to figure out how 8,000 turns into the area of this. It turns out that it's 5,120 pixels, which is not 5 to 4. If you took 8,000 and divided it by 5120, you would not get 5 to 4. You'd actually get 25 to 16, which is the square of 200 over 160. Make sense? Confused yet? Well, let's do a new one. Alright, say I have these two triangles. I know this one has a length of 16 here, and the area is 80. And I know I have this other triangle over here, which is similar. Let me just bounce this around so you can see it here. That angle's the same, this angle's the same, this angle's the same. In other words, we're told that it's similar. And I know this length is 16 on this triangle, and the corresponding length over here on this triangle is 12. And I know the area of this one is 80. So I know, that 16 times whatever this height is times a half is 80. Well, I don't actually even know this the fact that whatever this is, in order to figure out what the area is. So this is actually not important. It's kind of like Isabella. I don't really even care about that. No offense to anyone named Isabella. But if I know the ratio of lengths is, and you know what, I'm going to call that K. We talked about this back in the chapter on similarity. The ratio of lengths. K always has to be the length, or basically the one-dimensional ratio. It could be a ratio of perimeters, it could be a ratio of circumference, it could be a ratio of diameter, it could be the ratio of height. I don't care. It's a 1D ratio. Oh, this will help. It's a 1D ratio. 1D ratio would actually just be what we would call K, because what we're going to use for the area ratio, we need to take that number for K and square it. This is going to help a lot of people if I say it this way. the area ratio, or the 2D ratio, is the 1D ratio n squared. Well, okay, well, there we go. All right, the length ratio is 16/12. I don't like to leave it 16/12. People would laugh at me at math parties if I did that. I should call that 4/3. Okay, so what is k squared? Well, that's 4/3. Then we just have to square that. That becomes 16/9. So basically what I've said here is that this one is 4/3 times bigger. In other words, to go from this to this, I have to multiply by 4/3 to make it bigger. I always like my ratios of k to be bigger than 1, so I like to put the big number on top of the small one. You could call this 12 to 16 and go the other direction. That would be fine. In class, I'm always going to tend to go big over small. If I go big over small, I always have a ratio of k that's bigger than 1, so then I always know if I'm going to multiply that, things are going to get bigger. If I divide by that, things are going to get smaller. And it sort of helps to target the right direction. But really, it works either way as long as you're really careful about which direction you're going. So I like to be consistent for you, for your sake, so that we always kind of can predict what we're going to do with that number. Anyway, so I'm always going to make my k bigger than 1. All right, so k is 4/3. This thing is 4/3 the size of this thing. So the ratio of areas should be not 4:3, but 16:9. Notice how 16:9 is significantly different if you decimalize it than 4/3. That means that this ratio is not 4/3 of, this area is not 4/3 of this area, but it's actually 16/9 of this area. 4/3, and just to give you some estimation stuff here, 4/3 is like 1 1/3. 16/9 is closer to 2, so 16/9 is actually bigger than 4/3. This thing is, I don't know, maybe it's not as easy to see this in terms of area, but it's a different amount of like how much bigger than one is compared to the other, if we're talking about area versus length. Anyway, I'm rambling. Let's actually figure out this area over here, because the big question is, what is the area over here now, Mr. Smarty Pants, if you know all this other stuff? Well, if the ratio of length is 4:3, the ratio of area is 16/9, so this bigger area, this 80, is 16/9 times bigger than the area of this. So the area I'm looking for, actually let me call it, let's call it x for now. X is, I need to take x times 16/9 to make it as big as the other area, which is 80. Oh, I should be in red for answer mode. All right, x times 16/9 is 80, so x equals 80 times 9/16, which I can just about do in my head because 80 divided by 16 is 5. 5 times 9 is 45. So the area of this thing is 45. And a way to check that is to say, well, the ratio of areas then is 80 over 45. What? How did that little thing get there? All right, 80 divided by 45. If I reduce that fraction, guess what, kids? It's 16/9, which is what I needed. So, check. I guess there's really only one other type of problem they could give you on this, which is, okay, you got two similar figures, and yes, I created these similarly. You can tell all the angles are actually the same on these two wacky polygons. There's all the angles matched up. They give you the area of one, they give you the area of the other, and then they say, okay, they give you the perimeter of one. Oh, since we asked for the small one last time, we'll ask for the big one. So let's say the perimeter of this thing is, I guess I got to make it reasonable. Let's say the perimeter is like 42. I'm asking for the what's the perimeter of this one. Okay, well, I know the area ratio. The area ratio, and again, I like to make mine bigger than 1. The area ratio is 300 over 160. Yes, you could do 160 over 300 if you don't mind which direction your ratios go, but I like mine bigger than 1, so I like to put big over small. Some people like to put like new over old, or like, because I have a question mark here, I might want to do the one with the question mark over the one without the question mark. I don't know. I always like to do big over small, as I explained before. All right, but just be careful. We're not calling this the ratio k. We should be calling this the ratio of k squared. Why is this pen not working really nicely tonight? Maybe it's the rain. Can you hear the rain? I'm outside. It's raining. This is very surreal for me, living in the desert for 13 years. Okay, so k squared equals 300 over 160. We don't like 300 over 160. We want to reduce that fraction. I'll take off a 0 first, then I'll divide by 2. Is that going to get me all the way reduced? Yeah, I think so. The ratio of areas is 15 to 8. Well, that's k squared. I really need to compute with not k squared, but k. So the ratio of lengths here is actually this. It's the square root of that thing. If k squared is 15 over 8, k is actually square root of 15 over 8. So the thing I'm looking for here, oh, I should be in answer mode in the middle of my arrow. The answer here should actually be the 42. Think about this. I want this to get bigger. I made this so that this would be a number bigger than 1. So, of course, this is bigger than 1. So as I get, excuse me, as this is supposed to get bigger, I'm not going to divide by this. I'm going to multiply by this. I need to multiply by k. And I just figured out that k is the square root of 15 over 8. I'm not going to bother reducing the square root till it's time, really, which I guess is now. That this is like saying 42. Okay, now it's a matter of just computation reduction stuff. It's 42 times square root of 15 over the square root of 8. You could reduce this in a number of different orders. I guess I'm going to reduce this by doing the bottom simplification first. Then this becomes 21, square root of 15 over 2. I'll multiply that by square root of 2 over 2. Why do I make up such difficult problems? It's actually for your benefit, not because I'm some kind of cruel person. Okay. Yep, and then square root of 30, can that be reduced? I don't think so. It's factors of 30 are not square. There's a 5, there's a 6, there's a 2, there's a 15, there's a 3, there's a 10, but there's no square number, so I guess that's it. It's 21 square root 30 over 2. 21 square root 30 over 2. Okay, that's it. I went into some pretty difficult problems, actually. I'll see you in class.